this is first part of a two-part session, BGP 101, focus on BGP techniques for ISPs. So the first part is more the basics. The second part is the applicability, how it's applied. At the end of the session, we'll post, we'll upload the slide deck so you'll be able to access it. Feel free to ask questions, but just step into the mic and you can ask questions. So on the first session, the BGP 101, we'll discuss first the BGP basics, and then we'll discuss the scaling techniques and how communities are used in BGP. In the second section, we'll focus mostly on how BGP is used in ISPs, and in addition, we'll also discuss some BGP security related features. So on the BGP basics first, we'll discuss what BGP is, and then the BGP attributes, the different attributes of a BGP route, that is, and the path selection algorithm, and how different policies are applied with BGP using the BGP attributes, and we'll discuss finally the BGP capabilities. So BGP, as you all know, is a routing protocol. It is used to exchange routing information between different networks. Networks here is a loose term. So in this case, consider networks to be a collection of routers and systems that are administered by a single entity. It is exterior gateway protocol, so it's between different networks instead of within a network. It is described in RFC 4271, and there are several other RFCs that deal with BGP, but RFC 4271 is the main one. 4276 provides you with an implementation report on BGP, and 4277 describes the operational experience using BGP. Both of them are good readings. I recommend reading them. There are two IETF working groups primarily focused on BGP. The first one is Internet Domain Routing Working Group, and the second one is Secure IDR. The first one deals with BGP in general. Second one focuses on the security aspect of BGP. And later on, we'll discuss one aspect of that protocol, that features that focus on the security aspect of BGP. Autonomous system is the basic or the corner of BGP. Autonomous system describes a single network administered by a single entity, essentially. It is a number used to uniquely identify that specific network. In general, it is administered by a single entity. It's administered by a single entity. It's possible that a single entity may have multiple autonomous system numbers because of mergers, acquisitions, and so on. So autonomous system number is a collection of entities, routers, and networks that that run the same internal routing protocol, that have the same policy, routing policy. Typically, it uses a single routing protocol inside that network, but it's possible in some cases that some service providers use multiple routing protocols, and then they use BGP to bind those multiple routing protocols. Particularly if your network is large, that's possible. But in general, the core part of the network always runs a single routing protocol. But if it is a large network, a large service provider, the edges may be different routing protocols and then aggregated via BGP for internal use. Autonomous system is usually under a single entity, but as I discussed earlier, it's possible that a single entity may have multiple autonomous system numbers because of, again, mergers, acquisitions. It is identified by a 2-octet number, but since we are running out of that 2-octet number, a 4-octet number is introduced, and now you can have a 4-octet autonomous system number. And soon it will be very difficult to get a 2-octet autonomous system number, so you will have to use a 4-octet autonomous system number. So the 4-octet ASN was introduced by RFC 4893. So the 2-octet ranges obviously from 0 to 65, 535, which is to the power of 16 minus 1. And the 4-octet starts from 65, 536 up to the power of 32, which is that number. And the 0 and 6535, 65535 are reserved, so it cannot be used. 1 through 64,495 from the 2-octet space is typically used for the public internet. And then there are a couple of blocks for documentation, and there is 1 block for private use. And then there is 1 specific address, which is 23456, that's used to represent a 4-octet ASN within a 2-octet domain, particularly if that 2-octet domain or router or device doesn't understand 4-octet autonomous system number. And we'll discuss that later on. So the 32-bit range, which is a 4-octet range, is specified in RFC 5396. So this is for your reference, so it's good to go and refer them. It's defined as AS-plain, just as plain number, but it's possible to express into a dot format as well, instead of just a plain ASN. So the autonomous system numbers are distributed by RIRs, or the registries. You can, in some cases, you can also get them from upstream service providers. So as you can see here, from the current 2-octet autonomous system number, more than 63,000 has been assigned or allocated, and more than 40,000 are visible on the internet. Some have received 4-octet autonomous system numbers, but their use is not yet large as when compared to the 2-octet ASN. This is expected, since service providers may have older routers in their network, which may not be able to participate in a 4-octet ASN. So it will take some time for those devices to be purged from the network, and eventually, all the network will be able to deal with 4-octet, to support 4-octet ASN. So as you can see, about 8,000 has been assigned from the 4-octet space, and only 3,700 are visible. So over 3,700 are visible on the internet. You can see some of these numbers from those 2 links from the official INR site, as well as from the portal websites. So these numbers are changing. Obviously, if you look at the number 1 year down, it will be significantly different. But those numbers are current as of today, the one that you saw. So BGP basics, so you see that in this particular example, there are 3 different networks, and assume that these 3 different networks are owned, operated, and are administered by 3 different entities. And you see those AS numbers, even though in this documentation you are using 100, 101, and 102, the recommendation is to use those address ranges that are explicitly specified for documentation purpose. So that, particularly if you are providing configuration examples, you don't want people to copy paste it and create problems. So that's the reason why the documentation ASA numbers are there. But in this particular case, we have 3 different networks, AS100, AS101, and 102. So there are peerings between autonomous systems. So in this case, there is a peering between, you can have 2, it's possible to have 2 peerings between 100 and 101, on the top side and on the bottom side. And then 102 may have a peering with 100 and a peering with 101. BGP uses TCP for exchanging routes within a single autonomous system or between different autonomous systems. It uses TCP port 179. It is a path vector protocol, so it's somehow similar to, so it's not, as you know from IGP protocols, it's usually either distance vector or link state protocols. But in this case, the path vector is slightly different from distance vector. It's much more robust than distance vector, but it's also scalable. So we'll see what the path vector protocol means. It uses incremental updates, so which means whenever there is a change in routing, if a route is deleted, only that route is removed. Or if a new route is added, only the added route is sent, not a complete route is not exchanged unless a new peer is established. Or a peer is reset. That's the only case when you exchange the full table. If a route is changed, also only the updated, only that changed route is sent. But there is no any full route exchange unless you are starting a new BGP session or you are resetting the BGP session, the BGP peering relationship between 2 devices. So there are 2 types of peers, internal and external BGP, and we'll discuss them later on. So internal is within the autonomous system, and external is between autonomous systems, and we'll discuss them in more detail. DMZ within the context of BGP refers to the network that interconnects different autonomous systems. So in this case, you can see the DMZs are the bottom one network, a LAN network, and the direct connection at the top. So basically, BGP receives multiple paths from different autonomous systems or from different BGP speakers, essentially. If it has a peering relationship between this router and multiple other routes, it receives all those routes, and then it compares those routes, selects the base route, and then installs the base routes into the routing table, as well as advertises the base route into other peers. And we'll see when it advertises and to which types of peers it advertises routes later on. So base path is sent to external BGP neighbors. It's also sent to internal BGP neighbors. But there are conditions where it sends to internal BGP neighbors and when it doesn't, and we'll discuss that later on. The other very important aspect of BGP is it is heavily policy influenced. So service providers have different policy tools that they can apply to influence the routing selection decision. And we'll discuss those routing policies later on. So eBGP and iBGP refers to external BGP peering and internal BGP peering. BGP obviously is used both internally and externally, but in all of these cases, typically it's used to carry routers from the local network to the external networks and to receive routes from external networks. But for internal routing decision purpose, usually the IGP is used for the routing decision purpose. But as I mentioned earlier, when you have a very large internal network, you may also use BGP for that purpose as well. So iBGP is used to carry some of the internal prefixes, or it can carry all of the internal prefixes, depending on the specific service provider policy. Again, in some cases, those prefixes may not even be in the IGP, in the core IGP, because of scaling issue, particularly if you have a very large network. But it also carries the ISP's customer prefixes. Typically, if an ISP has customers, it's not advisable to install those prefixes into the internal routing protocol, into the IGP. It is highly advisable to inject them into BGP. So BGP is used to carry the customer prefixes within the autonomous system and also eventually advertise an aggregated version of those prefixes. But the types of routes carried internally and exchanged externally are different, and we'll see that also later on. So eBGP is used to exchange routes between different autonomous systems, and most of the routing policy is applied there in terms of filtering routes received and sent, and also influencing the routing decision, manipulating the BGP attributes to influence the routing decision or the route selection. So here is a model representation of the BGP. So you can see here we have 4 different networks or autonomous systems, and within the autonomous system there is always IGP, and you will have iBGP peering between routers. Between autonomous systems, it's always eBGP. Okay, so eBGP is used between routers between different autonomous systems, and those routers who speak eBGP to other autonomous systems are typically called border routers. Typically, the border router should be directly connected to other border routers, either through a LAN switch or a point-to-point connection. There are cases where LAN switch is used or layer 2 switch is used, usually in a public peering case, or in other cases, almost always a point-to-point link. It could be Ethernet, which is typically the case nowadays, but it's usually a point-to-point link if it is a bilateral relationship, peering relationship. You don't want to run IGP between 2 different autonomous systems. Okay. As a result, the requirement is the 2 routers speaking eBGP have to be directly connected. Obviously, there are exceptions to the rule, and you can have different connectivity mechanisms to interconnect 2 border routers, for example, in over a layer 3 VPN network and so on. But Typically, that's the exception, and it's not recommended. The typical connection is over a direct point-to-point or a switched network. So the internal BGP peering, and here also the term peer is used in to mean two different things. One, it's used to mean a BGP relationship between two equal, roughly equal autonomous systems to exchange their own routes. But in other cases, it means any type of BGP peering or BGP session. So that may be a little bit confusing, but I want you to be aware of that. So a peer might mean two service providers peering to forming eBGP session to exchange routes without exchanging money. So that's one meaning of peer. Another meaning of peer is just iBGP or eBGP session. Okay? So you may see both terms in different scenarios. So for iBGP, there is no need to have a direct connectivity between two routers. The connection between the routers is taken care of by IGP. So there is no need to have a direct connection, and it's not possible to have a direct connection because, as you will see later on, all routers within a single autonomous system have to be fully meshed or fully connected with all other routers within the same autonomous system. And there are ways to avoid that. We'll discuss that later on. But since that's a fundamental requirement, obviously it's not possible to have direct connectivity between iBGP speaking routers. Some of them may be, but in most cases not. Okay. So it's not a requirement to have direct connectivity, connection between iBGP speaking routers, but it is important to have that direct connection between eBGP speaking routers. Any questions? Okay. Again, here is an example of a three router. Actually, there are four routers. In this case, we have three iBGP sessions. So the third router, C, is not in the iBGP mesh. So when you have that scenario, that router cannot become a transit router for traffic going from another autonomous system, crossing this autonomous system to another autonomous system. For it to be transit, it has to participate in iBGP peering, full peering. Okay? But as long as you take care of that requirement that router does not become a transit, you can still avoid having iBGP session for some routers. And some service providers do that. Actually, most service providers do that. For the edge routers, they do not participate in iBGP peering because they do not become a transit router. So depending on the hierarchy of the routing, it's possible not to have iBGP session for all routers within a single autonomous system, as long as those routers do not become transit routers. Okay. Very important for iBGP peering is it's very important to peer using loopback addresses instead of physical interface IP addresses, because the physical IP address will disappear if the corresponding port or link goes down. On the other hand, the loopback IP address never goes down as long as the router is up. So it's important to configure a loopback address and use the loopback address for iBGP peering. Okay. Any questions so far on basics? So the next session is BGP attributes. there are different attributes. When you say BGP attributes, it means attributes of a route. There are different attributes that are advertised along with a BGP route. Not all of them are required. Some of them are mandatory and well-known. Some of them are well-known but optional. Some of them are transitive and do not have to be understood by other, by all routers and so on. But the attribute is the basic mechanism by which route selection is influenced. So one of the attributes is AS-PAS. So AS-PAS is a sequence of ASs that you have to traverse to reach that particular route. For example, in this particular case, to reach 180.10.00.16, a router in AS500 has to go through AS300, AS200, and AS100. So the AS-PAS for that particular route, as it appears in AS500, will be 300, 200, and 100. So the last one is where the prefix is originated, and the first one is the directly connected, the direct AS neighbor. Okay. It is used to influence route selection. Usually, if it is a longer path, a longer AS, you do not want to use it, or you prefer a shorter path. But there are other also requirements. So we'll discuss the route selection mechanism later on. But one of the uses for AS-PAS is for influencing route selection. Second one is for loop detection, and we'll see that later on. And the fourth one is for applying policy. For example, I may prefer a route going through a specific AS autonomous system, or I may prefer a route that does not go through a specific autonomous system. So you can apply policy to exclude those prefix or to less prefer or more prefer a route that goes through a specific autonomous system. So as a result, they are used also for applying policy. Okay. So earlier we discussed that autonomous system number could be a 2-octet number, which is running out, or a 4-octet number, which would be the future. So if you have a router that doesn't understand a 2-octet, a 4-octet ASN, the advertising router that understands a 4-octet ASN will replace the 4-octet ASN with 2, 3, 4, 5, 6. So in this case, for example, AS 80,000, 70,000, and 90,000 are 4-octet ASNs because they are more than 65,000. 4-octet ASNs, since they are 4-octet ASNs, AS300 understands 4-octet ASN, but AS400 or router within AS400 doesn't understand a 4-octet ASN, in which case the advertising router will replace the 4-octet ASN with a 2-octet specific ASN number, which is 2, 3, 4, 5, 6. Okay. So as you can see, for example, for prefix 180, 10, 0, 0, 16, the 70,000 and 80,000 are replaced by 2, 3, 4, 5, 6. So you see 2, 3, 4, 5, 6 twice because of that. So the loop detection. So how do we use AS-PAS for loop detection? The rule is very simple. If you receive an advertisement that contains your own ASN, then drop it, because it means it is a loop. So it detects the presence of a loop, so it drops that advertisement. It doesn't install it, or it doesn't advertise it. So that's how the loop prevention is done. So this is loop among autonomous systems. So there are other techniques for loops, BGP loops within a single autonomous system. But this loop prevention is a loop, prevents a loop that can be formed without the loop detection across multiple autonomous systems. Another important and mandatory, well-known and mandatory attribute, BGP attribute, is next hop. So the next hop is the IP address that will be used to forward traffic for that particular BGP prefix. So if it is an eBGP peering, the peer address is the next hop by default. And we'll see that we change that using a policy into something else, but we'll discuss that later on. But typically, if it is an eBGP peering, we use the peer address as an next hop. That's always the case. But when that particular router advertises that route to another iBGP peer, it doesn't change the next hop. The next hop remains the same. So in this case, for example, for a prefix 150.10.00.16 received in AS300 by the first router, router B, the next hop is obviously 150.10.11. But even router C, which receives that updates from B using iBGP, will have the same next hop. This has implication. The implication is that C has to know how to reach that particular prefix, which is 150.10.11, the link between A and B. So B has to advertise in IGP or through some other mechanism that particular prefix into the internal network. But typically that's not advised, and we'll see how we avoid that later on. But by default, iBGP updates, when a router sends updates to an iBGP peer, it doesn't change the next hop. The next hop remains the eBGP peer that advertises the route. So if you inject a route from a local prefix into BGP, for example, in this case, router B is injecting that local subnet, which is 121.10/24 into BGP, then the next hop is going to be the loopback IP address, which is used for iBGP peering. Okay? So when it injects that route into IGP, it uses the loopback IP address as the next hop. And the reason is because the loopback IP address is used for iBGP peering. That's the recommended. That's not a requirement, but that's the recommended, and that's the practice. Remember here, so when a router sends updates to an iBGP peer, if it is a local prefix that's injected by the local router, it uses the loopback IP address as an next hop. But if it is a route, if the route is received from an eBGP peer, by default it will not change the next hop. The next hop will remain to be the eBGP peer address. So there are differences between the two. Here's another one that's rarely used. This is called third-party next hop. It's rarely used, and usually it's not good from a policy perspective. But by default, if C has eBGP peer with A, and if A has eBGP peer with B, and if that peering is over a shared network, then when A advertises routes received from C to B, it will keep the next hop IP address of C. It will not use itself as a next hop IP address. That's the only exception used when routes advertise it over eBGP. But in general, we don't normally advertise a route received through a shared network to another router. Usually you don't do that. And if you do, you still have to use yourself as an X hub. From a policy perspective, normally that doesn't happen. But the default behavior is the third-party Next hub is kept. Okay. So Next hub best practice. So by default, as I discussed earlier, for external Next hubs to be propagated unchanged to be IBGP peers. So if you receive a route from external eBGP peer, the Next hub is not changed when it's advertised over IBGP. But you can override that using a configuration. On a Cisco router, you say Next hub self. In most other vendors also, it's the same command. Use Next hub self when you advertise to IBGP peer, which means the loopback IP address of the border router becomes an Next hub instead of the eBGP peer address. And that by doing that, it avoids injecting the network that's connecting that particular border router to the external peer. So by doing that, you are actually stabilizing your IBGP network, your IGP network, because it doesn't depend on the flapping or stability of that particular link. Also, it reduces the load on IGP. So the best practice always, usually the best practice to do Next hub self, which means instead of keeping the eBGP peering address as an Next hub when it's advertised to IBGP, you override it with Next hub self. Okay. So in summary, the Next hub IP address should be carried using IGP. Otherwise, other IBGP speaking routers will not be able to know how to reach the Next hub. Typically, you don't want to inject the directly connected interface into IGP. So to avoid that, you have to override the Next hub using Next hub self. By doing that, IGP will make the decision how to reach to the border router. Okay. Any questions on Next hub? Next hub is an important attribute, and it's always mandatory. It has to be there always. ASPAS may not be there, particularly if you are advertising to an IBGP peer for a locally originated route. There is no ASPAS. You only advertise ASPAS when you are advertising to external routes, external peer. You add your own AS to the list when you are advertising to external peer. Okay. So the next attribute is origin. Origin is more of a historical attribute. In that before BGP, there was a protocol called EGP. So to differentiate between EGP and BGP, obviously if a route is originated from an EGP, it will have EGP as the origin code, but there is no any EGP speaking router, so typically you don't use EGP. But there are two other values, which is the origin could be IGP or unknown. It is basically depending on how you inject the route into BGP. If you redistribute the route into BGP, it is called unknown. The origin is considered to be unknown, which means less preferred. If it is injected using a network statement, then it is called the origin is referred to as IGP, and it is preferred. Because if you inject using a network statement, you are explicitly injecting a specific prefix, and it is typically good for stability. But if you are injecting using redistributes, you are probably injecting a lot of routes, which may cause flapping and so on. So it's usually less preferred. Obviously, again, BGP is heavily policy influenced, so you can override the origin of the particular prefix using a policy. So it's not fixed, set in stone. You can always override most of this using a policy statement, including the next hop. You can override it using a policy. So it is a transitive mandatory attribute. IGP is preferred over EGP, and EGP is preferred over incomplete or unknown. So actually the right term is incomplete. Obviously EGP is no more there, so the two values are incomplete or IGP, and IGP is preferred over incomplete. Aggregator, so this is, it's possible that you can configure a router to aggregate a set of prefixes and inject an aggregate for those prefixes. You can inject both the aggregate and the specific routes, or you can just inject only the aggregate. When you do that, the aggregator, the router that aggregates the route, those prefixes is also added as an aggregator. This is mostly, it's not used for routing decisions, but it is helpful for debugging. So it's mostly informational instead of influencing routing decisions. Another very important attribute is local preference. So local preference is used to influence the exit point from an autonomous system. In this particular case, for example, you receive routes 160.10.00/16 through two different peers into AS400, either going through AS300 or going through AS200. If you look at from the AS path perspective, both of them are equal. So you probably, it's basically a toss, or there are tiebreakers that you use. But if you want to make a decision that I would prefer, as long as the peer is alive, I would prefer going through 300, you can use local preference when you receive the route. When you receive the route from 300, you can say, this has a higher local preference than the route received through AS200. So by doing that, the traffic that will go to 160.10.00 will exit through AS300 instead of AS200, as long as that peer is there. When that peer goes down, then it will go through the AS200. So the local preference is used to influence exit points. So in this case, as you can see, we are setting a higher local preference going through AS300 over the routes received through AS200, which is 500 and 800. So the 800 is preferred. Local preference, a higher local preference is preferred over a lower local preference. So as a result, the traffic will go through AS300. So in summary, it is a non-transitive optional attribute. So it only exists within AS. You don't advertise local preference to your eBGP peer. It's only within a single autonomous system. So when the route is received on the border router sets the local preference, and it advertises that local preference to all its to iBGP peers, but the peers will not advertise to an eBGP peer. So it is local. It's non-transitive. The default for Cisco is if you don't set a local preference, the local preference becomes 100. To set a local preference, you have to use a policy statement to say routes, this set of routes will have this local preference. So again, it influences exit points. Another one, another attribute is a multi-exit discriminator. In some cases called metric, but the formal name is multi-exit discriminator. This actually, even though it says exit discriminator, it actually influences how a traffic is received into your network. So for example, in this particular case, let's say S201 advertises 120.68.10 with a multi-exit discriminator of different values for the two different exit points. By doing that, going to the next one. By doing that, for example, in this case, it is setting 2,000 advertisers to C and 1,000 advertisers to D. Unlike a local preference, a lower made is preferred than a higher made. In the case of local preference, a higher local preference preferred over a lower local preference. But made is considered as a metric, so a lower value is preferred. So in this case, the path through D is preferred, which means traffic destined for 120.68.10 into S201 will come through B instead of A by setting the made value, by setting a lower made value through B. Again, obviously, A, the upper S200 can decide to change that policy using local preference. And local preference has a higher preference or a higher influence than multi-exit discriminator, and we'll see that later on. But obviously, when you do this, the two service providers have to have an agreement. They have to say, I'm going to use multi-exit discriminator to influence how traffic is coming into my network, and they have to agree on that. If they don't agree, then it may not work, because the two service providers may use inconsistent policy. So it's very important to have an agreement between the two to have a consistent policy. Okay. So you see that it is coming through B only. So again, multi-exit discriminator is between autonomous systems, not within autonomous system. Obviously, the multi-exit discriminator is carried with, after it is received by a border router, it will be advertised to all IBGP peers, but it will not be, that value will not be advertised to another service provider. So if a made value is received from one service provider, that value will not be automatically propagated to another service provider. You have to set a different made value to the other service provider, because it's only used to influence how traffic is received into a particular S. And again, the lowest made is preferred over a higher made. Okay. Another important aspect for multi-exit discriminator is, by default, only made values received from the same S is compared. If I receive routes from two different S's, then the mades are not compared by default. Obviously, you can override that using a policy and say, compare made always. If you do that, then it will compare the made values from different S's. Again, some confusions here. It's possible to have, the standard wasn't clear on the default value for metric, whether we should always advertise a made value or not. So because of that, different vendors implemented it differently. So some vendors may decide to send made value by default. Some vendors, and they may decide to the default to be 0 or the default to be higher value. And some vendors may decide if a route is received without a made, it's considered to be a very high made, or in some case a very low made. So because of that, it's very important to understand what the different vendor made values, made defaults are, or use configurations to override the defaults. But it's very important to be aware that vendors have implemented differently in that respect, because the standard wasn't clear on that. Obviously, there are configurations and knobs to influence it one way or the other. or most vendors provide those knobs. So one of them is always compare made. Another one is consider missing made as worst, and so on. So there are configurations to override those default behaviors, vendor default behaviors. Another very important attribute is community. So community is used to group different prefixes, BGP prefixes. You would create different communities and then make different BGP prefixes to be member of different communities. Then instead of dealing with individual prefixes, you will deal with community attributes. So you can say all prefixes that are members of this community, I will do this, I will prefer this, or I will not advertise them, or I will advertise them with a lower preference, or with a higher preference, and so on. So it makes the dealing with policy much easier than just dealing with prefixes. And we'll see why that's the case. So community is a 32-bit integer. It's usually formatted as S number and then specific community value. And the S number is usually the S number of that service provider. So if so it could be, if the service provider's ASN is 100, then the communities will be 100 colon something. So the meaning of the communities is different depending on the value of the community. So here is an example. Let's say you don't use any communities. So in this case, what you do is when you receive routes from S100, you say, I will receive this, and then you do explicit permit to receive it. And then on outgoing advertisement from E to F, you explicitly allow that prefix. Obviously, if there are two, it's easy. Let's say we add some more prefix now, received from AS200. Now, when I add that prefix, I will have to add another filter to allow that prefix to go to AS400. So now the configuration is not just one place, you have to apply it to multiple places. Okay? So this is just a simple example, but the power is really powerful in terms of how you influence policy, and you'll see that also through some of the examples, real life examples later on. Now, because of this is not scalable. As you add more routers, you have to touch several other routers to allow a specific prefix from a specific customer or peer. Okay. Now here is just extending again, adding more prefix. We added one more prefix, but we don't want to allow that prefix to go out. So we didn't allow it to go out on that peer. So using community, you can simplify this by saying that when we receive that prefix, we say attach community 300:1. Again, 300 is the S number for that S. Now, on that peer, you just say allow 300:1. On the outgoing E to F, you just say allow 300:1. And that will allow that prefix. Allow community 300:1. Now, when we receive another route here, you just attach, you just make it a member of the same community, and it will automatically be allowed on the top one because that community is already allowed or using a policy. So when you receive another one, which is 300, that one, but you don't want to allow it to go out, you make it a member of a different community. In this case, 300:9. Since we only allow 300:1 on the top, it's automatically blocked. It's possible that a prefix may belong to multiple communities. So, and it's usually the case. A prefix belongs to multiple different communities which have different functionalities. There are well-known communities. Some of the well-known communities are no export, and that's the value for no export. No export, we'll see what no export means. No advertise, that's no advertise. No export subconfig, another one, and then no peer. We'll see some of them, but some of them, since we haven't discussed about confederation, we cannot discuss about confed, and we haven't yet discussed about peers from this meaning perspective, so we'll not do that, but we'll touch on the no export. No export means don't advertise to another autonomous system. So if, for example, if A sends a route, two different routes, if A receives two different routes, advertise two different routes, in this particular case, it's advertising an aggregate 105.700/16 and more specific components of that aggregate. There are several of them, but it wants to advertise them to that AS200, but it doesn't want to propagate it to the rest of the internet. To do that, what it does is it advertises the top one without the no export community, which is the aggregate, but the more specific prefix advertised with no export. So when AS200 receives it, it will use it internally within AS200, but it will not advertise to any other autonomous system, to any other eBGP peer. So because it has a no export community attribute. So that's a predefined value. Okay. Another one is no peer. No peer means a peer is, as I alluded first earlier, a peer has two different meanings. One is any BGP session, but another one is a BGP session between two different autonomous systems that exchange their own network, but that are not used for transit to another network. And usually it is settlement free, which means they don't exchange money. They just exchange routes and send traffic to one another, but they don't use one another as a transit. So that type of relationship is called peer. So no peer means don't advertise this prefix to a peer. That's the meaning of it. So when you do that, you can apply a policy on a peer session to block those communities or those prefixes with the no peer community attributes. Okay. Now, earlier we said that communities are usually numbered using a colon notation, AS number followed by a specific community value. Now, but this assumes, again, communities typically are 32-bit. So if it's 32-bit community, how can you use it in a 4-octet ASN with 4-octet ASN? If you have a 4-octet ASN, what should be the first one, the first octets for the community attributes? So there are different solutions. One of them is just use a private ASN number instead of a 4-octet ASN number or a 2-octet ASN number. Another one is use the AS trans AS number, which is 23456, to represent a 4-octet ASN. But both of these have problems. The first one, it's not, it may conflict with other service provider ASNs because they may use the same private ASN number. Second one is it may conflict with other service providers because they may be a 4-octet ASN and you are using the same first part. So the reason the first part is specified as ASN is to make it unique between service providers or between autonomous systems. So the third option is instead of using the standard community attributes, use extended community attribute, which has more fields, a longer field. Okay. So the 4-octet ASN is use the extended community attribute instead of a specific community attribute that's assigned for octet for the 4-octet ASN. And that's specified in that RFC, 5668. So going forward, that will be the normal use. So instead of using a normal community, it will be extended community. Again, communities are optional attributes. And some implementations always advertise communities to their IBGP peers. Some of them do not advertise unless you explicitly say advertise communities on through configuration to IBGP peer. The same thing with eBGP. Some of them by default advertise communities over eBGP peers. Some of them do not by default, so you have to explicitly configure it. In the case of Cisco, on IBGP, it is the default behavior to advertise communities, but on eBGP peers, you have to explicitly say advertise communities. Otherwise, the community will not be advertised. So it's very important to understand those specifics about vendors, because the standard doesn't explicitly say always advertise. The default is advertised on IBGP peer or on eBGP peer. So it's up to the vendors to interpret it. So there are different interpretations or different choices, not so much in terms of interpretation. So it's very important to understand those default behaviors. Okay, so BGP path selection. I'll go through the path selection process. So the first is, if the route doesn't have next hop or the next hop route is not reachable, then it will not be considered. If you receive a BGP route and you check the next hop and you don't have the next hop in your routing table, then you don't install it, you don't advertise it. Also, if the made value is maximum, which is 232 minus 1, then it's considered not usable, so you don't use it. Then comes the preference. In the case of Cisco, there is a local router-specific attribute, so it's not really a BGP attribute. That's advertised to another peer. It's just local to that router. There is a weight that has a higher preference than any other preference. So the weight. So if a weight is configured for a specific prefix, that weight will have a higher preference than any other preferences. So the next one is local preference. So local preference is very influential. So if you remember, local preference determines how traffic exits on autonomous system. So that, again, a higher local preference is preferred. The next one is preferred locally originated routes over routes received from other peers. So if you originate a route, if a router originates a route, then that's preferred over route received from other peers or other sessions. The next one is the length of the AS path. If the AS path length is shorter, then that's preferred over a longer AS path. Obviously, you can ignore it. So in most of these cases, there are policies to configure to influence the decision. So you can say, ignore AS path comparison. I'm going to use something else to compare routes. Next one is origin. We discussed origin earlier. IGP is preferred over incomplete. Then EGP is not there in picture anymore. Made is, lower made is preferred over a higher made. Obviously, there are some knobs. Made is only compared for routes received from the same autonomous system. If you want to compare it for routes received from different autonomous systems, then you have to override it using BGP always compare made. Then the next one is prefer eBGP paths over iBGP paths. So if a router receives the same route, one from iBGP peer, another one from eBGP peer, then the route from the eBGP peer is preferred over the route from iBGP peer. Obviously, considering all the others are the same, or all the previous comparisons are the same. The next one is the path with the lowest IGP metric to the next hub of the BGP route is preferred. And the next one is, if that's the same, then the lowest router ID is preferred of the originator. And then if there are multiple router reflectors in the list, then the cluster list, the shortest cluster list is preferred. And then lowest IP address number for the neighbor is preferred. So in a multi-vendor environment, make sure the path process is understood each brand. So there are some variations between brands and then defaults also, as we discussed earlier. So some may, for example, advertise made, some may not, and so on. So you have to understand that and avoid the made confusion. Applying policy with BGP. So any questions on the BGP attributes and path selection? Okay. So now let's see how a policy is used to influence how traffic is routed, or which is called typically traffic engineering. You can steer your traffic to go through this way or that way, or to come through this way or the other way. So almost nobody just does the default configuration and get done. That's almost not the case, particularly on eBGP peers. There's a lot of policy implemented to filter routes, to influence path selection. So you want to control who you peer with, which means with the service providers that you are peering with, you only advertise your own routes. You don't advertise somebody else's routes. You also select who to transit, to receive transit from, or to become transit to somebody else. So you also want to influence traffic flow to avoid congestion. If one of your links is congested, you want to move traffic away from that congested link and use some BGP techniques to move traffic from that congested link. And remember, BGP is asymmetric. The way traffic enters your network and the way traffic leaves your network are different. So you have to apply different policies to influence those inbound traffic as well as outbound traffic. Policies are applied by setting attributes, the attribute values, by filtering prefixes. You only allow prefixes to be sent or received to certain peers or customers or transits. By prepending ASN numbers to increase the length of the AS path, you can prepend multiple ASNs to just artificially increase the AS path lengths. By doing that, you can say, don't send me traffic through this unless this peer is down, by prepending a lot of ASNs on one peer. So most implementations have peers, but most of them have a way to define prefix lists or prefix sets, to define community sets, and then some kind of policy language to do if-then conditions, and based on some conditions to drop certain routes or increase, add some attributes or change some attributes and so on. BGP capabilities, this is also very important. When BGP session is established, one of the first things to do is exchange the capabilities of the two routers. If you remember earlier, we said that when two routers peer, if one of them does not understand 4-octet ASN and another one understands 4-octet ASN, then the one that understands 4-octet ASN has to replace the 4-octet ASN with 23456 when it sends that update to the 2-octet ASN. And the way it knows that that router doesn't support for-rotated OSN is not through configuration, but through the capabilities exchange. So when the session is brought up, they understand what types of capabilities are each side is capable of doing and not doing. So the capabilities are documented in that RFC, and the parameters are sent through the BGP open message. And there are some values 0 to 63 are assigned by INA, and 64 to 127 on a first come basis, and then 128 to 255 is for private use, vendor specific use. So some of the current capabilities are multi-protocol extension for BGP. Usually this is for supporting like IPv6, supporting VPN v4, VPN v6, and so on, multicast and so on. Another one is route refresh capability that we'll discuss later on. Outbound route filtering capability, multiple routes to a destination capability, and so on. Multi-pass capability, and so on. So we'll discuss some of these capabilities in the next section, but there are several types of capabilities that are exchanged. So the multi-protocol extension, again, this is, as I discussed, this is for supporting exchange of, even though BGP was initially designed for exchanging IPv4 unicast routes, it's now used to exchange different types of routes and information, including VPN v4 routes, VPN v6, layer 2 VPN, VPWS, multicast, MDT3s, and so on. So there are several other types of capabilities that BGP supports. So that's the multi-protocol extension. Route refresh, and we'll discuss that shortly. 30-bit support, we already discussed that. And there are some other capabilities in development. So scaling techniques. I'm going to go a little bit faster. We are running a little bit short on time. So scaling, BGP scaling techniques, we'll discuss about dynamic reconfiguration, route reflectors, and BGP confederation. So when BGP was first designed, it was very small. So BGP has grown so much. So scaling is very important, and the community works a lot to make sure that the internet is stable and scalable. And there are different techniques and standards that were implemented. So we'll discuss some of the, one of them is the route refresh. Another one is configuration templates. These are vendor specific, but most vendors provide some kind of template to reduce the configuration overhead and improve the scalability. Update groups, that's also pretty much combined with configuration templates. It's typically, in some case, automatic, in some case, configuration driven. Route reflectors and confederations that we'll discuss. Route aggregation, which is very important, and we'll discuss it also. 4-octet ASN, because we are running out of 2-octet ASN. And then route flap dampening, but we are not going to discuss that, and it's not that much in use nowadays. Route refresh, when one of the problems with BGP, one of the problems is, let's say you apply a policy to your eBGP peer. Now you dropped some of the routes because of that BGP policy, and later on you change the policy. But since you already dropped, and since BGP is incremental, you will not be able to receive those routes that you have dropped from your peer unless you reset the session. And resetting a session is very bad. So what are the alternatives? One of them is the hard reset is very bad alternative because it's not good for the internet stability, and it's not good for your network in general. Another one is soft BGP peer reset without the route refresh capability. In this case, to be able to reset, to do soft reset, whenever you receive route from your peer, you will always keep those routes even if they are dropped. So which means you have to have another set of memories that keeps all the routes received from a peer. But that takes up a lot of memory, particularly if you are peering to so many peers and receiving routes, several routes from each one of them. So it doesn't scale well. So what the route refresh capability does is, by implementing the route refresh capability and the two routers, if the two routers are capable of doing route refresh, then what happens is when you change a policy, the system will automatically send a route refresh request to the peer, and the peer will send all the routes that it has and advertise all the routes to that peer. Now it will apply the new policy and then proceed with that. So that's the route refresh capability. So it makes it non-disruptive policy change, because without it, either you have to have the soft reset with a lot of memory requirement, or the hard reset, which is very disruptive. So for most implementations, you don't need to do any configuration, as long as the two routers are capable of exchanging capable of doing route refresh, they will exchange the route refresh, and no additional memory needed. But the peering routers have to support route refresh, and you have to make sure that they do. Otherwise, you have to implement the soft reset capability that requires memory. In some implementations, by doing that, you can say, if the route refresh is there, use the route refresh, otherwise use the soft reset that requires a lot of memory. This is basically a summary of what we discussed, so I'll go with the next scaling technique. So the next scaling technique is route reflectors. Earlier we said that all routers within an autonomous system have to have a full IBGP mesh, particularly if some of those routers are going to be used for a transit. If it is not going to be used for a transit, then you can exclude it from participating in BGP. But if it participates in BGP, it has to have full IBGP peer. But that doesn't scale. As you can see here, if you have 1,000 BGP, 1,000 routers, then the scale will be almost 500,000 IBGP peers on the network, and that's a lot of peers. So to avoid that, we can use route reflectors. And the way, the way the route reflectors work is when you select a couple of routers as route reflectors, and then everybody peers with those route reflectors. Now, the route reflectors change in behavior. Typically, when an IBGP peer receives a route from one IBGP peer, it doesn't advertise to any other IBGP peer. It only advertises the route to eBGP peers. But with a route reflector, when a route reflector receives routes from an IBGP peer, it will advertise to other IBGP peers as well as to other non-IBGP peers. Sorry, to other clients as well as to non-client IBGP peers. Obviously, it will also advertise to eBGP peers. If it receives routes from a non-client peer, IBGP peer, it will advertise to clients only. It will not advertise to other non-clients. So that's how a route reflector is different from normal IBGP router. You can have multiple route reflectors. Obviously, you need to have multiple route reflectors for redundancy. You can also split the network into multiple domains, and each one of them will have their own route reflectors, and then the route reflectors can peer with one another using IBGP again. Route reflector uses originator ID for loop prevention. So if a route reflector sees its own ID within an IBGP update, it knows that it was originated by itself, so it will drop it. So that's how the loop avoidance works. Again, redundancy is important. Usually, you will divide your network into clusters. Each route reflector will be its own cluster, typically, and you use the router ID as a cluster ID. So normally, clients will connect with two different route reflectors for redundancy purpose, and those two route reflectors will be in two different clusters. So here is an example. In this case, even though it shows two clusters, since there are two different domains, you can think of them as 6 clusters in this case. But you can also make it just 2 clusters. But in this particular case, since we normally use the router ID as a cluster ID, in this particular case, you have 6 clusters because you have 6 route reflectors. But the important is each client peers has IBGP session to 2 route reflectors in 2 different clusters. So the benefit is it solves the IBGP mesh scaling issue. It doesn't impact packet forwarding. It does impact it a little bit, but not much. A route reflector, one of the decision criteria for BGP paths is if everything is equal, then the IGP metric for the next hop is used. So the IGP metric view of a route reflector may be different from an IBGP metric view of the client. So because of that, there is some variation, but it's not significant. So it's worth having the route reflector to avoid the scaling issue. And it's easy for migration. So typically, it's always because of that, because the route reflector view of the IGP metric, you want it to be consistent with the view of the clients. It's important to have the route reflector topologically in the path to all the other routers. It's not always possible, but it's better to try to have it in a topological center to avoid that IGP metric view discrepancy. So the typical migration, so this is dealing with migration. Typical migration is core routers have fully meshed BGP. So the core routers will have full mesh BGP, or the core, if you use the core routers as route reflectors, they will have full IBGP mesh. And then the edges will have IBGP client peering to the core routers. That's one example. So let's say here the core routers have full mesh, and we started from there, and basically you identify 2 route reflectors. Let's say if you have a small network, you identify 2 routers as route reflectors, and you start establishing IBGP peering with those route reflectors. Once that peering is established, you can remove the full mesh peering later on. So it is gradual, it's easy to migrate. Okay. The next one is BGP confederation. In the same way as route reflector, BGP confederation deals with the IBGP mesh issue, but it deals it in a different way. What it does is it subdivides the network into smaller networks, and each one of them are considered as a sub-confederation or a sub-S of the big S. So, so it divides the S into sub-S's. Each sub-S will have IBGP peering within the sub-S, and there will be eBGP peering between sub-S's. But that eBGP peering between sub-S's is not visible externally. It's only internal to that network. Again, in the same way as route reflectors, the whole of the confederation has one IGP network. So it's probably better to go through the example. Here's an example. So in this case, AS200 is split into 3 sub-confederations or sub-ASs, 65530, 65532, and 65531. So typically, the private ASN number is used as the confederation AS number or the sub-confederation AS number. So in this particular case, confederation 65532 is configured to peer with other subconfederations 65530 and 65531, and it's configured with the AS number of the whole network, which is the BGP configuration identifier, is the ASN number of the network. So when there is eBGP peering between C and external network, it will use 200 as the ASN number for that network. So one of the key in confederation is the next hop is not changed when it's advertised from one sub-AS to another sub-AS, unlike other eBGP peering. A normal eBGP peering, when you send it from one AS to another, the next hop is changed. In subconfed, the next hop is not changed. The local preference as well as made are not changed either. But there will be a confederation AS paths, the AS paths, as you can see here, 65002 and so on. But when it is advertised to external routers, that will be removed. That's only for internal within the confederation. So route propagation decision is pretty much the same, except that we remove the local preference made and next hop as kept as they are. So in summary, to compare the two, both of them deal with the scaling issue, the full mesh scaling issue, and they are hierarchical. There's policy control for both of them, but in terms of scalability, route reflector scales very high compared to confederation. It's easier to migrate. So in most cases, route reflectors are preferred, and most of the implementations use route reflectors instead of confederations. But confederations allow absorbing other service providers into the network. So because of mergers and acquisitions, some service providers went through the confederation path instead of route reflector. And you can still use route reflectors within a confederation. Okay. Any questions? Okay. So I'll start this topic, and then we'll break soon. The next section is not as broad as is not long, so I will include some of this session to the next session. So BGP communities is another scaling techniques, and we have seen that. So I will jump straight into some of the examples. So here is one example. So here are two examples, customer edge and internet edge. Let's go through the customer edge example. In this particular case, let's say a service provider has 3 different types of connections to the internet. Peers, which means exchange free settlement free peer or BGP session, eBGP session. Another one is private peering. Again, that's also settlement free. Another one is transit provider. So they have transit provider. So for their customers, they can provide access either to the whole internet or just to some of their own peers. Obviously, when they provide access to the whole internet, since they are paying the transit provider, they will be incurring costs. But if they are sending it only to the peers, then their cost is minimal compared to sending it to the transit provider. So they may charge their customers accordingly and then classify their customers accordingly based on that relationship. So in this case, for example, so for IXP connections, that's for peering connections, it uses community 100, 2100. For private peer, it uses 2200. And for internet peering, it doesn't use any community. So it gives the whole internet. So customers who buy just IXP, they will get 2100. So they will only get routes from 2100 with community attribute of 2100. And customers who buy private peering as well, they will receive the 2200 community. But customers who buy the whole internet, they will not get community, which means they will send to the whole internet. So that's how these three different types of customers are implemented. So using community simplifies that configuration. Otherwise, you have to classify each prefix of the customer, and doing that will not be scalable. Another example is the the internet edge. So in the internet edge, so the first one is the peering applied on the customer edge. In this case, the community is applied on the internet edge. So in this case, the customers are classified into customer. So the peerings are classified into customer, IXP, private peer, and transit provider. And by doing that, they basically filter prefixes going to the peer based on these attributes, community attributes. So here's an example. So customer prefix. So if customer wants to send other customers, they will receive 3000, community 3000. If they want to send to receive traffic from IXP prefixes, then they will receive 3100, and so on. Again, the use of both of these cases is, instead of using explicit prefixes or applying policy based on explicit prefixes, you group them into communities and you apply the policy based on communities. So that way, you only make the changes on whatever you are adding. If you are adding a new customer, you only make changes to that particular customer configuration. You don't go and make changes to other points in your network. Any questions? Okay. So in the next section, I'll go through some of the communities. I'll just review a little bit of this. Some of the communities that are used by service providers to influence different routing decisions. So I'll cover that in the next section. Any questions? Okay. Thanks. So the next session will be in half an hour.